So we're going to return to our discussions about atomic classes and operations, and we're going to dive a little deeper into some of the infrastructure topics related to atomic operations and variables and classes. And we're going to start by discussing the Java memory model, and then we're going to talk about how the Java atomic operations let concurrent programs have access to lock-free, thread-safe mechanisms to read and write to single variables. Those are the two things we're going to talk about here. So what is the Java memory model? So the Java memory model is something you can actually read about here. This is a summary of it. I think it probably provides a link to more information. It's defined in the Java language specification. And it basically carefully specifies the semantics of what's supposed to happen when multiple threads share fields in shared memory. And now keep in mind, what does it mean to be shared memory in this context? This is shared memory within a process. Remember, a process in the context of Java is a unit of resource allocation and protection. So you can allocate things in a process like memory objects. You can allocate things like handles to shared files. You can allocate threads. There's various things you can allocate in a process, and processes are protected from each other so that threads in one process can't accidentally corrupt the state of fields and other resources in another process. And then within a process, you can have multiple threads. So when you have multiple threads in a process, they're sharing that process's memory, and the memory model kind of defines the semantics of what should happen in terms of how do you want the behavior, what should the behavior be. Now, you might ask the question, why the heck do we even care about this stuff? Well, you wouldn't care about this stuff if you only had single-threaded code. You wouldn't care much about the memory model at all. But when you have multi-threaded code, things get really tricky. And the reason they get really tricky is because modern hardware, especially multi-core hardware, is trying very hard to optimize the hardware, hoping that that will make your systems run faster. So it's going to come up with all kinds of ways to make things run at the hardware level just as fast as it possibly can. And one of the consequences is that you can have instructions that appear to be sequential in one thread, and the side effects of those instructions will appear in different orders in other threads in that process running on a multi-core processor, which is very non-intuitive when you first see it. The reason for all this stuff is to make things run really fast. And so it's the purpose of synchronizers and, of course, the Java memory model to guarantee certain things if you don't want the memory operations and the instruction operations to occur in sort of random orders. It's kind of like, why do we have traffic lights? Why do we have stop signs? Why do we have all these rules of right-of-way and who gets to go first? To try to keep people from just, killing each other on the roads. Same thing is true here. So we have all these rules that are defined in the memory model in order to allow programs and programmers to give ordering when ordering matters, but when ordering doesn't matter, we want the hardware and the software infrastructure to make things as fast as possible. And there's a bunch of things that'll reorder stuff. So the compiler can reorder stuff, the just-in-time compiler can reorder stuff, the processor caches can reorder stuff, and so on and so forth. So let's take a look at some examples to illustrate this concept of instruction reordering. So here's a simple example. We've got, X and Y are fields that are assigned to 0, and then thread 1 and thread 2 are going to run in parallel or concurrently, and they're going to do several things. Thread 1 is going to set X to 1, thread 2 is going to set Y to 1, and then thread 1 is going to read the value of Y, and thread 2 will read the value of X. And so the question that you might ask yourself is, what are the values of I and J after this code is executed? Well, it turns out that if you don't have any synchronization in your code and you just write this code and you run your program lots of different times, it might end up that after these two instructions run, I equals 0 and J equals 0. Even though you would think that X was set equal to 1 and Y was set equal to 1, both these things may end up being 0 just based on the order in which the fields are cached and the order in which those caches are flushed from one core, one thread running on one core, to another thread running on a different core. So that would be pretty non-intuitive if your program gave you strange results each time you ran it. And you also want to the memory model also says what the output should be if the virtual machine is implemented correctly. So here's another example where we have same kind of thing. We set R1 equal to X, R2 equal to Y, and then again, we're kind of doing these things. And we don't want to have just like random results, right? The results should make some coherent sense. So you don't want it to be the case that after doing these operations, the result is just some crazy number like 42 that has nothing whatsoever to do with anything up here. That would be rather strange, but it turns out that with larger types, like things that are 64-bit in size, that you can actually, if you're not careful, have the words split in such a way that the first half of the word will have been set to a value, and the second half of the word will not have been set to the same value when you did it. So those would give you very strange results. In my personal opinion, reading the Java memory model specification is incredibly dull. It's really, really, really boring. And so some people want to know every last nuance of this, and there are people who need to know this stuff, namely the people who write the Java runtime environment. They need to understand this, but most of us mortals don't need to understand it. So the good news is, as long as you follow the rules and make sure that any fields that are shared within a process by multiple threads that can run, say, on a multi-core processor, you access those fields always under the proper protection of the different synchronization mechanisms we're talking about: mutual exclusion mechanisms, atomic mechanisms, barrier synchronizers, coordination mechanisms, and so on. As long as you're careful in how you use these synchronizers properly, for the most part, you don't have to know or care about all the subtleties of the Java memory model, which is good, right? This only becomes an issue if you're trying to be really cute and clever and you're trying to super duper optimize your code. So as long as you don't do that, you'll be in good shape. There are people who know how to do that, and they're typically the ones writing the lower level Java libraries and the lower level Java concurrency utilities. All right, so that's a really quick overview of the memory model. Again, the key thing is the memory model defines what the semantics should be, and they're trying to be as generous as possible to allow optimizations, but they provide you with these wonderful synchronizers to get control when you need control. And you normally need control if you want some kind of sensible behavior in your concurrent programs or parallel programs. So, having said that, there are then a whole pile of Java atomic classes, and they're in a package that's the Java util concurrent atomic package. If you take a look at that package, you'll see a bunch of atomic classes like atomic long, atomic boolean, atomic integer, and so on and so forth. The atomic variables like atomic boolean, atomic long, atomic integer, instances of those classes are the atomic variables. And they provide so-called lock-free, thread-safe operations on single variables. And we'll see what lock-free means. Lock-free basically means ultimately they're going to use compare and swap operations that don't end up actually having to acquire a lock. They just sort of spin until they get their way. For example, atomic long is a very powerful class, very popular class for this kind of thing. And it provides various atomic compare and swap operations and other operations that are built on top of atomic compare and swap. And I'll talk more about that in a second. There's also something called long adder, which can be used for like counters. You might want to keep track of, I don't know, the number of times people access content in a website, and you want to do this very efficiently. And all you care about there is that the results will be eventually consistent. You don't care at any given point in time what the actual count is, because you're just keeping statistics that need to be recorded on a per hour basis. And so they have a very efficient way that works when you have high contention with lots of threads, with low overhead. So let's take a quick look at some of the atomic operations. At the core, these atomic operations are implemented in hardware, and then the underlying Java operating system and execution environment, the virtual machine and so on, provides you with encapsulations of what's available at the hardware level. The most common mechanism, we've kind of talked about this before, is the compare and swap. I'm showing you a C-like implementation of this. This would not be Java. It's not even necessarily strictly C. It's just showing you kind of the idea here. So compare and swap atomically compares the current contents of a memory location. So here's the memory location. It's a pointer to some memory location. and it checks to see if the value is the expected value, and if the value is the expected value, it atomically updates it to the updated value, and it returns the old value. So let's take a look and see how this works. So the first thing is there's an atomic section here. So this is done atomically. All that means is that all of these things execute inside start atomic, end atomic, or nothing does. It's all or nothing, and this is implemented by hardware operations. I'm just showing you the pseudocode that would exist if you were to write it in C. So the first thing we do is we take a snapshot of the old value here and store it into a local variable. And if the old value, in other words, if the current value equals the expected parameter, if it's what we think it is, then we atomically update the location to the given new value, but only if it's the same. If it's not the same, it doesn't do that. And in either case, it returns the old value. So we always get the old value back. Now, we may or may not have updated things. We'll see. Here's an example of using the compare and swap operation to implement a spin lock. This would be a busy weighted spin lock, a lock-free operation, because it never locks, it just spins. So we're going to give it this mutex, which is a pointer to some memory location, and we're going to implement a mutual exclusion mechanism using a spin lock. You can see the spin is the while loop. So while what we're saying here is this is the value we want it to be in, 0, which means it's available. This is the value we want to update it to, which is 1. So when we call compare and swap, if the existing value, if the old value was 1, which means available, then we will atomically set that, if the old value is 1, then it's used, it's in use. So we're going to keep spinning. So you can see here, compare and swap will check to see if the mutex value is 0, and if the mutex value is 0, it'll set it to 1 atomically, and it'll always return the old value. So if it was already 1, then it wasn't available. And because it wasn't available, we have to keep spinning. So what this is saying, a higher level way to read this loop is keep spinning while somebody else owns that lock. While someone else has that location of memory in use, keep spinning. That's the way to read that thing. And only when we were able to find it having the value of 0 available, we will then atomically set it to 1. So in that case, the old value would have been 0, and we'll break out of the loop. So that's how we lock the lock. So the lock is now held. And then the way we unlock it is we come in with that location of memory, somehow magically ensure mutual exclusion, and then we're going to go ahead and set that location to 0, and then release the lock, or make it unatomic. I shouldn't have said release the lock, because we're implementing a lock. This is just an atomic region. And this is the part that, of course, will be done in hardware through whatever means is necessary to do it in hardware. So this is going to atomically set the value to 0, such that this code here will return 0 instead of 1. And so we would be able to get this thing at that point. There are other ways of doing this. Compare and swap is the most general way. There's also something called test and set, which is a bit simpler. And it's the same basic idea. The main difference here is that we're not going to be able to compare something with an expected value and then update it to an updated value. All it does here basically is check to see whether or not the value was 0 before, whether we locked it or not. Yeah? Good question. Yeah, so I think the question you're asking here is, let's say we have 2 different mutexes, then 2 different threads could simultaneously, acquire those 2 different mutexes as long as they're not shared. So as long as they're not the same mutex, those things could run in parallel. And the reason that's important is because you're using the mutex to provide a critical section for a particular piece of code that has to have exclusive access, mutually exclusive access to something. And if you have 2 different things that are sharded or somehow split, then as long as they don't share anything, they could run in parallel. That's a great question. So test and set is a simpler version of compare and swap. And the main thing is it just goes ahead and sets the value to 1, and it'll return the old value. And so you can use this basically in a similar way. So, while the thing is locked, keep spinning. That's what that's saying. And only when it's available are we going to be able to get it. So this is actually a somewhat simpler piece of logic, but as we'll see, it's not quite as powerful. And so for the most part, people use compare and swap rather than test and set as the basis of the hardware instructions. So if you look at, say, Intel, they use a compare and swap hardware primitive that then all these other things are layered on top of. And that's why compare and swap is, quote, better, because you can set the value to something other than 0 or 1. And that will actually turn out to be significant when we look at some of the Java semantics in these atomics classes, in the atomics package. Okay, so a couple examples of human known uses. I've used some of these before. So if you're a Star Trek fan, then you know what a transporter is, and you can convert a person into an energy pattern, which is then beamed to a destination and reconverted back into matter. Wouldn't that be great? We wouldn't have to worry about Nashville traffic, just transport ourselves around. Boy, think what you could do. You could stop dealing with carbon emissions, and you could have all the parking lots back. You just beam yourself around. Obviously, if you don't have atomic operation, if you leave half the person in the transporter room at one location and you beam half of them someplace else, you're in big trouble. I think that was actually some of the plots in the original Star Trek dealt with transporter malfunctions, where they split people up into 2 different personalities and all this kind of crazy stuff. So if you read this Wikipedia article about transporter accidents, you can find out when they didn't obey the atomicity properties of transporters. For those of you who are a different generation, you might remember the Harry Potter stuff. So apparition is the same kind of concept. That's another human known use. I guess it's really a wizard or witch known use of atomicity. So the way this works, for those of you who haven't read the books, is if you concentrate really hard and you know how to do the spells and so on, you can disappear from where you currently are and instantly reappear wherever you're trying to concentrate on. And if you remember one of the Harry Potter books, they're practicing this. And in fact, if you don't do it right, then you will splinch. And what will happen is part of you will be left, like your nose will be left somewhere, your arm will be left somewhere. And that actually happened to poor Ron Weasley. That's his splinching wound. And luckily they had teachers standing by to reattach him and stuff like that. So those are some examples of atomicity that are human known uses, even though they're a bit far-fetched.